In the last lecture, I told you about stars, which are giant nuclear fusion reactors that convert hydrogen to helium. In lecture 30, I'm going to review the evidence that the life cycle of a star depends on its mass. I have two main objectives in this lecture. First, after reviewing the last lecture on stars, I'll begin by examining our own star, the Sun, in some detail. I want to give you a feeling for our special knowledge about this nearby star. Then I'm going to put that discussion in the context of the present state and the ultimate fates of all different kinds of stars, from very large to very small. We're going to meet some very strange characters along the way: white dwarfs and red giants, neutron stars, black holes. The study of stars inevitably leads us to the conclusion that the universe is a very strange and remarkable place. So first, let's review what we've learned about astronomy and the study of stars. In the last lecture, we saw that astronomy is the science and the art of collecting photons. We measure four properties of these photons: their wavelength, their intensity, the direction to the photons in space, their variation. We do this in the hope that we can learn something about stars, about the direction to the stars, about the composition of those stars, their motion, their temperature, their brightness, their mass. Astronomers have a large and an ever-growing array of land and space-based telescopes that now peruse the heavens in all different wavelengths, from radio waves to gamma rays. As astronomers peer into the heavens, they find that almost everything they see are stars. Countless billions of stars in the process of being born, of living out their lives, and dying. Stars can be characterized by their position on a Hertzsprung-Russell diagram, a diagram that plots the star's temperature versus its total energy output. Now recall that the star's temperature is measured by its color. Red stars are relatively cool with surface temperatures that may be no more than about 3,000 degrees, whereas the hottest stars, the blue-white stars, may have surface temperatures of tens of thousands of degrees. The Hertzsprung-Russell diagram also plots on the vertical scale the total energy output of the star. And this is measured by a combination of the star's brightness, how bright it appears to us, and our knowledge of its distance. There are 10 orders of magnitude difference between the brightest stars, the most intense energy-producing stars, and the dimmest stars, those with the lowest energy output. One major discovery of the Hertzsprung-Russell diagram is that most stars, including our own Sun, lie on a broad band, a diagonal band, which is called the main sequence. The main sequence includes all the stars that primarily burn hydrogen. We see from the Hertzsprung-Russell diagram that the Sun is a rather ordinary star. It lies right near the middle of the Hertzsprung-Russell diagram, right smack in the middle of the main sequence. There are many stars that are hotter and many stars that are cooler. There are many stars that produce more energy, but many stars that produce a lot less energy than the Sun. Now I want you to think about the life of the Sun. Our star can't burn forever. The mass of hydrogen in the Sun is admittedly immense, but day by day that mass is diminished. 700 tons of hydrogen a second is consumed. So someday the Sun's energy has to run out. Studies of the Sun, combined with observations of the life and death of many, many other distant stars, reveal the likely ultimate fate of our own solar system. Because of its closeness to us, the Sun is by far the most thoroughly studied star. Not only can we see it easily, but there are several solar observatories that are dedicated entirely to studying the Sun and its properties. So let me review briefly some of the information we've learned about our own nearby star. First of all, the Sun is a sphere of hydrogen. It's about 700,000 kilometers in radius. That's more than 100 times bigger than the Earth's radius. In fact, it's about equal to the radius from the Earth to the Moon. So if you place the Sun over the Earth, it would extend all the way out to the Moon's orbit, or almost. Now in cross-section, we know the Sun has several different layers. Almost all the energy produced in the sun by fusion takes place in the core. Hydrogen burning in the core takes place in the central 10% of the sun's volume. And that's the region where the temperature and pressure is highest. Energy has to be transferred from the core through the thick layers leading out to the surface. And this occurs primarily by radiation in the central part of the sun. That radiation moves from plasma to plasma to plasma throughout the sun, and it takes a long time. It can take hundreds of thousands of years for the sun's radiant energy to go from the core to the outer layers. In the outer 200,000 kilometers, the outer mantle of the sun, you have energy transferred by convection. In this case, huge swirls of plasma convect in giant cells, and this is a more efficient way, a more rapid way of transferring energy from the inside of the sun to the outside. But the total energy transfer process can take hundreds of thousands of years. When we look at the sun, what we see is the photosphere. That's only the outer 150 kilometers or so of a transparent atmosphere of the sun. This is the zone from which the sun's energy radiates out into space, coming to us at 186,000 miles per second. In fact, it only takes 8 minutes or so for the sun's energy to reach us from the surface, but it's taken hundreds of thousands of years to come from the center to the surface of the sun. Now, the surface of the sun is a violent place. It has magnetic storms, eruptions of plasma. And we can see those surface markings with solar telescopes that tell us a great deal about the dynamics of that violent outer regions. Now, there are other layers of the sun as well. During a total eclipse of the sun, this is when the moon passes in front of the sun's disk. In that very brief event, we can see the sun's hot, glowing atmosphere, which may extend more than 1 million miles into space. In addition to light from the sun, we learn about that star from its solar wind. There's a constant stream of hydrogen and helium ions. These are positively charged atoms that have electrons that have been stripped off of them, and they stream outward from the sun, propelled against the magnetic field of the sun. This wind can be measured in outer space. You can also measure it at the moon's surface, and you can actually collect particles, hydrogen and helium atoms, that have come to us from the sun in the solar wind. One important effect of the solar wind is that these particles interact with, they distort the Earth's magnetic field. The intensity of the solar wind varies. At its peak, it causes the northern lights, which is that colorful glowing band of ionized particles. Very similar to fluorescent lights, by the way. The solar wind's composed of ions. These are charged particles. And these charged particles can often disrupt satellite communication and other kinds of radio communication. My father, an amateur radio operator, talks about days when the sun is well behaved and days when the sun isn't well behaved at all, depending on how strong that magnetic flux is. Well, now that we've seen some of the distinctive characteristics of our own star, we can return to the more general question of the lives of all different kinds of stars. Our intimate knowledge of the sun, combined with those telescope observations of countless distant stars, allows us to model the life cycles of all these different kinds of stars. And here we have to look to theory to help us with models. Theoretical models reveal that the lives of stars are a constant battle, a battle between the force of gravity pulling mass inward with incredible force, and the radiative pressure. If you think of all the nuclear reactions that are going on, the radiation pushing outward, holding the sun outward. And so a star has to achieve a balance between gravity pulling inward and the nuclear fusion processes pushing outward. Computer models of the sun are therefore very complex. They have mathematical equations that represent matter and energy, the forces and the motion of that matter. These computer models have to merge information from all sorts of disciplines, from nuclear physics, from plasma physics, of course, because the sun is a plasma, from fluid dynamics, the motion of fluids, from cosmochemistry, which tells us something about the composition of the sun's interior, and much, much more. These models are constrained by all sorts of Earth-based measurements. For example, the size of the sun, the mass of the sun, the temperature, the energy output. These are important constraints to all theoretical models. Now, what modelers do is they set up a series of equations that treat the sun as a radially symmetric object. There's a series of thin shells on top of each other. Now, the sun is not necessarily precisely radially symmetric. The sun is rotating on an axis, so the poles may be somewhat different than the equator. But from a modeler's point of view, for the deep interior of the sun, these concentric shells work quite well, and they're mathematically simpler. You estimate a starting temperature, a pressure, a composition for each of the layers, and then you have to assume that the first law of thermodynamics holds, energy is conserved, that mass is conserved, and so forth. And you just let the sun take off with known equations of how mass and energy behave. The model then predicts how temperature and pressure and composition, layer by layer, varies over time. The evolution of the outermost layers, for example, reveals how much radiant energy comes to the Earth, and that's a very important thing to know. Well, there's some major conclusions of these models, and they're quite fascinating. One of the major conclusions is that when the sun formed 4.5 billion years ago, it was much less bright than it is today. Indeed, it may have only been 70% of its current brightness, 70% of its current total energy output. Well, this leads to what has been called the early faint sun paradox. The paradox that if the sun was that much cooler, the oceans had to be solid ice when they formed. And we'll explore that faint sun paradox in more detail in Lecture 54. The energy output of the sun over time gradually increased. Indeed, it's gradually increasing today, although not at all noticeable by human standards. Just very, very gently, the sun is moving up from the lower right to the upper left of the Hertzsprung-Russell diagram, just slightly producing a little bit more energy every 100 million years or so. Now, modelers estimate that the sun's going to continue this stable hydrogen-burning phase for perhaps several billion more years. It's going to continue to gradually increase in brightness. But perhaps the most significant aspect of these models is how constantly the sun has shone for billions of years and how constantly it's going to continue to shine. This is why most of the stars lie on the main sequence. Most stars are in a stable phase where gravity pulling in and nuclear reactions pushing out have balanced each other and form a star that remains more or less stable for a long period of time. If we look at the Hertzsprung-Russell diagram, we'll see then that most stars lie on the main sequence. Most stars spend their lives burning hydrogen. But there are other kinds of stars. They're the red giant stars in the upper right-hand corner of the Hertzsprung-Russell diagram, stars that are extremely energetic but quite cool at their surface because they're so large. And then there are the white dwarf stars in the lower left portion. These are stars that are extremely hot and yet have very little energy. Somehow they're extremely small stars and very hot stars. So this suggests that there are other processes that eventually have to come into play. Something else besides hydrogen burning must be going on in some stars. And that's a key to understanding the history and the future of stars. Now, I want you to remember throughout the ensuing discussion that the stability of a star depends on this countering forces of gravity pulling in and nuclear fusion pushing out. Let's face it, all stars have to eventually run low on hydrogen fuel in their core. That's inevitable. So let's look at the sun. In the final stages of the sun's life, helium concentrations build up in the core. And hydrogen burning must therefore take place farther and farther out in concentric layers around the core. When that happens, two things result. First, because the hydrogen burning is closer to the sun's surface, it causes the sun to expand. There's less pressure farther out, and so those nuclear reactions can cause the sun to balloon outward. And when this happens, the first thing that goes is Mercury. Mercury is going to be engulfed by the sun some billions of years down the road. And then the sun keeps ballooning outward. Eventually, it surpasses the orbit of Venus. Now, fortunately for Venus, the sun's not actually going to engulf Venus because as the sun balloons outwards, its solar wind increases, and so much mass is flung out into space, the sun loses mass, and so the orbit of Venus naturally gets farther and farther away from the sun. It's an amazing coincidence. But then, so Venus moves outward as the sun moves outward. The Earth is going to move outward a little bit as well. All the planets will, because the gravitational force of the sun will be diminished. But at some point in this dramatic transition, Earth will become absolutely uninhabitable. The temperature at the surface of the Earth is going to have to climb and climb and climb as the sun's surface gets closer to us. This is perhaps in 1 billion or 2 years, nothing that any of us have to worry about. You can follow the history of the sun on a Hertzsprung-Russell diagram. For most of the billions of years of the sun's history, it lies very close to the main sequence. But when the hydrogen in the core has been burned up, it starts to expand. It gets larger and larger. It still produces lots of energy, but as it expands, it actually gets cooler at the surface because all that energy is coming out of a larger surface area. You burn for this way for a long time. Now, note that this process takes the sun away from the main sequence. It takes it towards the upper right of the Hertzsprung-Russell diagram. In fact, as a result of hydrogen burning around the core gets hotter and hotter, you get more and more energy produced, all the remaining hydrogen in the core is consumed, and then you go into a stage of helium burning in the core. And this is a major transition in the history of the sun. The helium nuclei fuse. They form heavier nuclear. Most notably, 3 heliums combine together to form carbon-12. This is the process of helium burning. Well, the consequence of this is more and more energy is being produced by the sun. It expands outward, and that's when the sun becomes a red giant star. A red giant star, the stars that are in the upper right-hand corner of the Hertzsprung-Russell diagram, is indeed a helium-burning star. Now, for a sun-sized star, a star like our own, carbon is absolutely as far as fusion can go. You can't fuse to make anything heavier. So once the core becomes carbon, the nuclear processes in the core slow down. And at that point, the sun's history changes. You can follow this progress again on a Hertzsprung-Russell diagram. So you have the main sequence for billions of years. Then you have hydrogen burning in outer layers. The star gets larger and actually gets cooler in its surface. But as helium burning clicks in, then the energy and the temperature of the surface gets hotter and hotter. When the helium burning stops, then something really dramatic happens. The star starts to collapse. Gravity starts taking over. The star begins to get smaller. And when a star gets smaller, you start adding energy to the star because gravitational potential energy, which is causing the star to be large, is transferred into heat as the star gets smaller and smaller. So here, the primary energy input is not just nuclear reactions, it's also the transfer of gravitational potential energy to heat. A star is getting smaller and it's getting hotter, and its energy output is staying more or less the same. And this happens for some period of time until you reach the ultimate stage of gravitational collapse, when all the nuclear fires go out. When helium burning ends, when hydrogen burning ends, the sun no longer has nuclear fuel to keep it going, and it starts collapsing and collapsing and collapsing some more. The nuclear fires are out, but a huge amount of gravitational potential energy is converted into heat. And this causes the white dwarf star. Incredibly hot star because of all that released gravitational potential energy, but virtually no nuclear reactions are going on anymore. And so the white dwarf star shrinks down to something perhaps only the size of the Earth. And that star continues to shine, slowly getting cooler and cooler, radiating its life out into space. The second law of thermodynamics applies to stars, after all. If you have a hot object in cold space, heat transfers from hot to cold. So what we see on the Hertzsprung-Russell diagram, what we see in our telescopes, are all these different kinds of stars that are typical, a part of the sun's life cycle. Main sequence, red giant, white dwarf. So now at last we're ready to examine different sizes of stars and see their ultimate fates. The smallest stars are about the 10th the size of our sun. These are called brown dwarfs, and the reason they're called brown dwarfs is because they really don't get very hot and they don't get very bright. Think about what that star must be like. These small stars burn their hydrogen very, very slowly, and thus they don't radiate very much energy to the surface. They just appear as dull red stars in the heavens. They are in the extreme lower right-hand part of the Hertzsprung-Russell diagram, cool, low-energy stars. but they last for hundreds of billions of years. Now, because brown dwarfs are so faint, they're very difficult to detect with ground-based telescopes. And this is one of the reasons we want to have orbiting infrared or heat-seeking telescopes. Heat-seeking telescopes have the best chance of locating these objects. It's very likely, with the number of brown dwarfs growing rapidly, that we may find nearby stars. Some of the closest stars may be so far undetected brown dwarf stars. So let's go to the other end. Stars that are more than a few times more massive than the Sun experience a very different fate than that sequence of red giant white dwarf. Larger stars have several concentric layers of fusion reactions, different fusion reactions going on inside them. Going deeper, because the temperatures and pressures get higher and higher, you may find hydrogen burning to produce helium-4, but then layers of helium burning to produce carbon-12. And as you go deeper and deeper, stars that are 10 times more massive than the Sun are going to burn up all their hydrogen fuel in perhaps 100 million years or less, and then they have to resort to other kinds of fusion reactions. After you get to carbon, you go to oxygen-16. Oxygen-16 burns to neon-20, to magnesium-24, and so forth, all the way up to iron-56. And you've heard of iron-56 before, the ultimate nuclear ash. The last of these steps of fusion can take place in a matter of seconds in a star. The final stages of fusion burning in a star are very rapid. And then what happens? Then you have a core of a star filled with iron-56, the ultimate nuclear ash. You can get no more nuclear energy out of this material, and suddenly it's like the rug being pulled out from under the star. Gravity is pulling in, nuclear reactions push out, you turn off the nuclear reactions, and all that's left is gravity pulling in, collapsing the star. Incredibly powerful forces pulling all of that immense mass down to the center. In an instant, the star explodes. It implodes and then rebounds out into space in what's called a supernova explosion, an explosion of unimaginable power. And in the process, nuclei of all different sizes are formed by fusion. You cram so many atoms together that they start sticking together, and all of the elements of the periodic table are formed in an instant. The leisurely processes of nuclear fusion in stars build up these smaller elements up to iron, element 26. And that's as far as you can go in a star with fusion. But then in an instant, when that star explodes, everything else, all the heavier elements, silver and gold are formed. All the elements that we think of, lead, bismuth, vanadium, all of the heavy elements are formed in an instant. Uranium, plutonium. All of these come from exploding stars. If you have gold jewelry, if you have a gold wedding band, every atom in that material was formed in an exploding star billions of years ago. Now, when a star explodes, the matter is flung out in all directions, and the universe is seeded with these new concentrations of elements. We now have dramatic photographs from the Hubble Space Telescope of ancient stars that have exploded and are still expanding clouds of all these debris of the chemical elements floating out into space, ready to seed the formation of new stars. Now, the fate of any star a few times larger than the Sun is that it's going to explode. It's going to become a supernova. But often when a star explodes, it leaves behind a smaller, but nevertheless quite massive object that marks the place of the former star. And these remnants are among the strangest, the most bizarre objects that we know of in the universe. If you have a remnant mass more than a few times that of the Sun, it collapses down into an incredibly dense object, an object in which electrons and protons fuse together to form neutrons. Now, this is just the opposite of beta decay. Remember, in beta decay, a neutron became a proton and an electron? In a neutron star, the protons and electrons merge together and form an object that may be 10 miles in diameter and have several times the mass of the Sun, composed entirely of neutrons. In effect, a giant nucleus. Now, neutron stars, because all that mass has been brought in, the star is rotating and it rotates faster and faster. Neutron stars can rotate very rapidly, thousands of times per second. And when they do this, because neutron stars have very strong magnetic fields, they can create signals, pulsing radio signals in space. As the star rotates around, as it sweeps around, the radio signals sweep by the Earth. And you can get very regular pulsing radio signals from deep space. These objects are called pulsars. Now, pulsars, when they were first discovered in 1967, were very enigmatic objects. And indeed, they were first mistaken for signs of life. It was felt that the only way that you could get a rapidly repeating radio signal was through some high technology. Well, the true nature of pulsars was soon deduced, but nevertheless, pulsars are given catalog designations of LGM in star catalogs, and that stands for Little Green Men. If you have a residual mass after a supernova of more than about 30 times the mass of the Sun, something very different takes place. The gravitational force is so immense that you collapse down to a neutron star and just keep going and going till all that mass disappears into a point. The point is called a black hole, an object so massive that nothing, not even light, can escape from it. And this represents the ultimate victory of gravity over the pushing out forces of the nucleus. The nuclei lose, gravity wins in a black hole. Now, black holes themselves are invisible. They absorb light, so you can't possibly see them. But you can see the effects of black holes in the surrounding space, and therefore we have ways of detecting black holes in space. One of the ways that gravitational black holes may be observed is by the fact that they often rotate around an adjacent star, in a binary star. And if the black hole is massive, the other star may have a stream of matter that radiates from one star, sucking it into the black hole. And these can actually be observed in space with telescopes. Another possibility is that black holes, being so intensely gravitational, they actually bend light from more distant sources. So if a black hole passes in front of a more distant galaxy, then you'll actually may see a gravitational lensing effect, where that object suddenly brightens and dims, or where it might actually you see a ring of material where before there was just a single dot. Well, I want you to think now, in conclusion, about the role of stars in our own lives. We usually point to the sun as the giver of life, the source of all the energy for the plants and therefore for us in our lives. And that certainly is a very important role of the sun, the conversion of hydrogen to helium to make energy, and the energy then sustaining life, is a vital role of of our sun and for stars in general. But we now see another role for stars that's absolutely critical in our own lives, and that is the stars are the factories of the chemical elements. You start with hydrogen, and you make the entire periodic table, and from that periodic table, all living things are brought. That's why Carl Sagan said over and over again, we are all made of star stuff. Well, in summary, our studies of the sun and of other stars reveal that the ultimate fate of stars depends on their mass. Stars that are much smaller than the sun are brown dwarfs. They're destined to fitfully fuse small amounts of hydrogen for billions, tens, hundreds of billions of years, never getting very hot, never getting very energetic. Stars the size of the sun enjoy billions of years of stable hydrogen burning, but eventually they're going to exhaust their hydrogen supply, and then they expand briefly and they become red giant stars, emitting huge amounts of energy but with a relatively cool surface. Inevitably, the helium burning stage ends and they collapse down to a white dwarf star, essentially a dead star that just gets cooler and cooler over billions of years. And then we have stars much larger than the sun, stars that end their lives as giant supernova explosions, littering the galaxy with all the chemical elements from which to build more stars. And we have the massive remnants of those stars, the strange neutron stars, and the black holes. In the next lecture, I'm going to continue our exploration of stars by considering the vast collections of stars, of billions of stars collected together to form galaxies.